Okay, so I want to kind of warm up with a little hands-on activity again. To just remind you first, so we got this orthogonal matrices when we were doing linear algebra before causal inference lecture. What were they? It's like an n by k matrix. Let's say n is bigger than k. And when you do Q transpose Q, it gives you the identity. So this type of stuff, if it would be n by n, that'll be only rotating things around, as we talked. It's just rigid motion. When it is n by k, it's like an orthogonal projection, okay? Now we will do a quick computation to make sense of what do I mean when I say orthogonal projection. Suppose you got a vector x, it's like sitting right here, okay? And then if I take this q, it's n by k. I cannot multiply q with x because the dimensions don't match, right? It's got k, x is n, you know, the dimensions should match to do any vector matrix. So I got to apparently take Q transpose, right? Q transpose is what? Let me write it. It's K by N, right? That's going. Now this N here matches with this vector, so I could do Q transpose X, okay? Now, whenever I do Q transpose X, so X was in Rn, right? Whenever I multiplied with Q transpose, since Q transpose is K by N, what is the output, this whole thing? It's going to have K dimensions, right? So you can already see this Q transpose is like reducing dimension, right? Okay. Now, if I do like Q transpose, I'm kind of back again in n dimensions, right? However, this is like looking n dimensional, but it's living in a particular part of n dimensions actually, okay? So this Q transpose X thing will be always in a smaller space that is spanned by columns of this Q. So imagine your Q like right here, okay? It was like n by k. It's like a tall and skinny matrix, right? And then look at its columns, right? Okay, let's say first column, second column, third column, right? And then take the span of those columns, right? So columns, they have n dimensions. Suppose this is 3, this is 2, right? I'll get like 2 columns. They have both 3 coordinates. But when I look at their span, it's going to be a 2-dimensional thing, okay? So this Q transpose X, okay, it's still got like n dimensions or 3 dimensions, but it's going to be always living in that small thing that is spanned by the columns of this Q, okay? It's in a particular place. Very good. Now, let's say I'm trying to find somebody that is in the span of these columns, and that is like the closest to my X, okay? And that should be like the projection of this X to this place, right? That's what was the projection was. Okay, fine. And then, and we were thinking this should be the projection. When we were talking, I'm just trying to remind you, okay? So if this is the projection, how would I know that? Okay, let's go slow. So anything, let me go step by step. Anything that is in the span of this stuff, it can be written as follows: Q times Y, where Y will be a k-dimensional vector, okay? Let me make this concrete. I'll get back to that. So let's say Q was 3 times 2, Q1, Q2. I got only 2 columns, right? And they got 3 coordinates, right? What is the span? Literally put a number in front of the first vector, put a second number in front of the second vector, right? That's about it. That's what you could do with these 2 vectors. Put a number in front of the first one, put a number in front of the second, sum them up. And this, if I would call this matrix Q, what I just wrote here would be Q times Y, where Y would be just that 2 numbers, right? It's going to be the same thing if you would have like K columns. We'll just pick K numbers, make it a vector Y, multiply it with the Q, right? Okay, so everything in the span of this stuff is written by Q times Y, where Y has K coordinates, okay? So Q times Y expresses everything in this like smaller dimensional stuff. Very good. If this thing is actually the projection, what needs to happen is like when I look at my X and I look at that thing Q transpose X, and when I look at anything else like QY, the angle between these two vectors should be right angle, right? So this represents, take anything on here, there, whatever, and draw a vector. This thing should be orthogonal to that. That's how you would have a projection, okay? Let's say if I steal like Farhan's notebook, and let's say I'm in 3D, and I have a projection right here. Now take any vector you like on this notebook. My finger should be orthogonal to it, okay? That's what's going on, if it is actually the projection. Now, how do I check if it is actually the projection? This vector is X minus this thing, X minus this thing, right? And this vector is that minus that thing. They should be, or when I take dot product, it should give me 0. That's how I could check the orthogonality, okay? Now that's gonna be your quick warm-up for today. Please compute this. And let's see if you get a 0. If you get a 0, then we all agree this is actually the projection. It's doing what it's supposed to be doing, okay? Before computing, any questions? Does the problem setup make sense? So I'm looking at this X minus this stuff is this vector right here. And QY minus this is this vector right here. And since QY could be any Y, this represents any vector you could put inside here, okay? If you always get this 0, that means actually this was like a right angle to the entire thing. That was literally the projection, okay? So we need, yes, go ahead. Very good question. So this was what I was talking about right here. So let's say Q say is 3 times 2, okay? And this is your first column, this is your second column, and you put a number here, you put a number here. This is how the span of these two vectors look like. Exactly. And then a generic thing is like, put 2 numbers right there, multiply that thing with Q. It's a generic stuff on that plane, right? In general, if you have K vectors here, if it is n by K, pick a generic Y with K coordinates, multiply it with Q. That's what it is. And I'm trying to check if my vector here is actually orthogonal to any generic vector on that plane. If that's the case, this is really the special thing. It's the closest I could get. Yeah. Okay, just check this out. And you might, you can use a little trick we learned before. Let me remind you that also. If you have something like this, like a vector here, let's say V, and a matrix here, say A, and another vector, I don't know, say W, this would be the same thing as A transpose V W, right? You remember that. So you can move a matrix from one side to other of an inner product by just transposing. Okay? Okay. I'll give you a minute or two to think about this. If you're not a big fan of doing this algebra, it's okay. I'm just trying to make you think through this being the projection. That's all my purpose now. Okay? You can also prefer to just remember that and go with it. That's your choice. Since I forget everything all the time, I have to reconstruct when I need it. Yeah, if you're somebody of that sort who wants to see why things are working out, this is useful. Yeah. Minus that point is this vector. So I don't know where is it. It's just somewhere on that plane. That's all I know. What I'm saying is like X minus that dot is this vector. And this dot minus that dot is this vector. And I'm trying to see the angle between the two vectors. That's all. Yes. Yeah, if this looks like a little weird, that's okay. You know, main thing, if you want to do data science a bit, more rigorous and seriously than just playing with some libraries, a big part of it is getting used to thinking about high dimensional vectors. If this is feeling weird, that's okay. That takes, that's part of what I'm trying to do. You'll get used to dealing with big vectors, and that's a big chunk of doing data science, actually. And we put this trick right here, or maybe here. I don't know. Yeah. So what do we know about Q is like, if you take Q transpose Q, that's going to give you identity. That's what we know about it. That's a different thing, right? I got Q times Q transpose right here. That's literally my projection matrix. And that's something good to be aware of. Q times Q transpose and Q transpose Q are very different animals. One of them is the identity. The other one is what takes everything and projects them down. This is the one that's going to help us. Very good question, Adam. Okay. And I was just playing with stuff here myself. Okay, I'll give you a minute more to think. Then, yeah, very good. Yeah. Let me see. Yeah, this is good. I think we can do it quicker though. All right, I think you guys are warmed up. Let me stop the pain, okay, and tell you how it goes. So, all right, so this is something here, and this is another thing right here. All I'm doing now is like taking this stuff into Q parentheses, like Q multiplied with Y minus that thing right there. Since this is Q times Q transpose X, if I put them into Q parentheses, that's how it is going to look like. So far, so good. Now I'm going to put that Q matrix to the other side. You're going to get Q transpose minus Q transpose Q, Q transpose X, right? And what is this thing? What is Q transpose Q? Identity, right? So this is literally, that goes away. This is just identity. And when you get rid of it, what do you see on the left? This vector minus the same vector. So that's a 0. And if you inner product anything with 0, you will get a 0. Okay, that's it. So this shows this thing right here, Q transpose X was the projection, because I started with whatever QY. Y didn't have any role in anything, yeah? And I ended up saying these two vectors are actually orthogonal to each other. Okay, and remember our discussion with the Pythagorean stuff. Being orthogonal means being the closest, and that means that this Q transpose X is actually what we're looking for. Okay, now you think about like this thing I draw here would be your model, and X would be the reality, and then this would be your model's best approximation to the reality. Okay, and the length of this vector right here, that's going to be your error. So if X was already on that plane, there will be no error whatsoever. You'll model perfectly. Okay, but if it is not on the plane, if it is a little above, the distance from your X to that projection is the amount of error you're making. Literally, how big is this vector? This guy right here is the amount of error your approximation is making. Okay, so far so good. Very good. Yeah, go for it. Question. Yeah. Because this is QQ transpose. This is an N by N matrix. This is Q transpose Q. It's a K by K matrix, and it's just identity. These two are very different things. Okay? These are very different animals. This is our projection matrix. This does the work for us. This is just the definition of this Q. It's just saying it's an orthogonal stuff. Think about like this guy is 3 by 2. This is a 2 by 2 thing. This is a 3 by 3 thing. Okay, very good. Any other questions so far? Okay, now we did this. Let's go back and recall our linear regression stuff. And then I'll move on to more matrices and PCA. And this will be our last linear algebra lecture. Whenever this discussion finishes, we will start probability. Okay, very good. It's okay. All right. Now this was our linear regression before going that. So now, how do we connect this Q transpose QX stuff? It goes like this. When somebody gives you an M by N matrix, Q, Y, I'm sorry, right here. Okay. Now I'm recalling stuff we talked about. But since it was a lot of concepts that we are going through, you know, I'm reviewing whole linear algebra in 3 lectures. That's all I could do for this course. So I think it's good to recap a little bit. All right, so I told you something called QR decomposition. We have some notebook on our canvas giving you, basic code to play with this if you like. And it's not the only decomposition in that notebook. There's 2 more. Okay, what is QR? You take a matrix Y, M by N, any matrix. You can always write it as Q times R, where Q is your orthogonal stuff, and R is an upper triangular matrix, okay? When you picture this, it's gonna look like this. This is your matrix Y. Here's a nice orthogonal matrix, and here's an upper triangular guy, N by N. And it could be very nice, like this upper triangular could be all the way going through the diagonal. In the case that your Y is actually full rank, okay? That's usually what we are gonna be dealing with. If it is, say, 3 by 2, and if these 2 columns there are just copies of each other, it's kind of lying, right? So it's like, I got 2 vectors, it's the same vector twice. Okay, that's not a nice situation. Then in that case here, you will see like an emptiness, right? Like 0, 0, 0, 0. Okay, but if it is not lying like that, here you would see like a nice N by N matrix going through the diagonal, R becomes invertible, things work out, okay? So far so good. This is what QR decomposition is. And we will use it for linear regression, projection, whatever else. Okay, now suppose we are actually in the case where the data is not lying to us, like in the sense that there are N columns here, they actually span something N-dimensional. If there are like 2 columns, they actually give you a plane, not a line, right? Okay, and in that case, this R will be invertible. And now suppose you're given an X and you want to find Y times something that minimizes the distance. So what I'm trying to say is like find this weights so that this distance is the smallest among all possible choices you have. And this is the problem we just solved. The solution is make this so that you get the projection there, right? But how do I get the Q? Well, wait, slow down. We had a Y, where did this Q come up, etc., right? So basically, this is what QR decomposition is gonna give to you. Just take your Y, it wasn't orthogonal, it was like a complicated matrix. Do the QR, you will see the orthogonal guy right there. And as soon as you see the orthogonal, you know how to project. It's the thing we just solved together, okay? And then for your Y, you will again do the projection using just that Q, and that's the right projection, okay? Yes. Yeah, exactly. For an orthogonal matrix, that R is not needed. It's gonna be just identity right there. Exactly, okay? That's the projection, yeah, exactly, that's it. So QQTX is what you're looking for. That's the closest point in this place to your X. and that vector is orthogonal, okay? And now, if somebody gives you y, not the qr, let's read through the correspondence, okay? So qqtx is gonna be y times this weights, and y is qr. Let me multiply with q transpose left and right. So q transpose q is identity. Q transpose q is identity. I got rv q transpose x, and at the end v becomes r inverse q transpose x. If you need that w, that weight stuff, that's right here. This is your data, this is your q, and this is your r inverse, okay? If that's what you need. Because, I'm sorry, if you're doing linear regression, people would usually want this one. They wouldn't want your q and x and whatnot. They will tell you, give me the weights. Give me the weights of the linear regression, okay? Because the way they would think would be the following. They would say, okay, whenever I see this weight stuff, I understand what's going on. Wow, what would they mean by that? So far, so good. Any questions? If there are no questions, I will erase this picture and explain why people would like to see that weight instead of q transpose x. It's the same thing, but just in a different language, okay? Any questions so far? Okay, so that weight vector, the way people would think about it. So as I said, y times the weight is nothing but the projection. So this is what it is, okay? But when they see the weight, it's easier to understand for them. Let's say this is my y. Y was m by n. Okay, and here's my weight. And now this is my proxy. This is my y times v. And this is my best approximation to the actual thing that is x. What does that mean? My model now is thinking, take the first column, multiplied with the first number right here. Take the second column, multiplied with the second number right here. Now third column, blah, blah, and sum it up. That's your best approximation to your x, okay? Let me write what I just said. My model is now thinking, so let me also erase this and put this up. So these two stuff here are the same thing, they're equivalent, all right? And now this means, in this perspective, this you can think about it this way. First weight times the first vector. Let me put an arrow to just emphasize these are vectors. And this stuff is just numbers. Okay? And then when they look at this, they would say, okay, if this number is much bigger than this, that means what this column represents is much more important for my model than the second. That's why people would like to see this one. Okay? It's a little more easy to have an interpretation of what's going on. Otherwise, it's just your projection. This and that are the same thing, okay? Now, even though mathematically this is what it is, I'm not suggesting take your gigantic data matrix, do the QR, and go from there, okay? This is mathematically what it is, but it's not algorithmically a clever thing to just do QR and use it all over the place. If your data is small, maybe that's a good thing to do. You will have much better ideas than just doing QR. But this is what's going on in the behind the scene. You're literally projecting a data on something linear. That's what linear regression is, okay? All right, since you're like projecting, doing Pythagoras, whatnot, they would call it least squares sometimes. You know, you have a vector minus another vector, you take the norm and you square it, right? They would sometimes call the least squares error or least squares model. You're trying to make the square the least possible. Right? All these fancy words just means you're projecting. That's about, right? So far, so good. Any questions? Let me see how is the time. Very good. So let me go back to linear regression discussion and actually show you this once more. Then I think I'll be done with this, and I'll do some other stuff. So in linear regression, we got the labeled data, right? This was our vectors, and this was the label, say features of a house and the price of a house. And we were trying to develop a linear model. And what was happening at the end of the day was like the error notion. You would see this RSS. It's something of like least squares error, something like that. Okay, I did not come up with this. If you see this literally means your model's prediction minus the actual thing, square it, sum it up. Okay, that's what it means. And then you want to minimize this error. Okay, then it ends up being exactly the story we talked about. The solution comes up as follows. Your best prediction, I think we went through this last time. Let me give you the final result. You don't have to go through it once again. The final result ends up being your X transpose is your data matrix. You do the QR for it. X is your gigantic data matrix. Y is the labels. Every vector here has just one numbered label. Every vector is like all features of a house on Zillow, say, and the number next to it is its price, okay? And you stack up all that houses into one matrix. And now you're trying to find the best weight possible to predict the price. You know, first feature, I don't know what, square feet. Second feature, what was the fancy thing they come up with? Curb appeal, you know, like whatever it is, you know, all that features, and then you put some weights on it and you try to predict the price, right? Okay. And literally what's going on is like, take your label vector, project it down on the span of your data columns. Okay, that's what's going on. And it makes sense because the number of data columns is the same as the number of labels you got. Every column has one label, right? Okay, that's your best linear approximation. And the weights you will see will be like this. As I said, this is your label vector. This is your Q. This is your R inverse. This is the weights of your linear regression model. That's literally the same thing as projection. But as I said, I'm not suggesting take your gigantic data vector and do the QR and go from there. No, don't do that unless your data is very small. But this is what's going to happen whichever algorithm you run to fit your linear regression. Okay. Now, to actually show you the algorithms that you would use, we need to discuss some optimization. I need to tell you what is gradient and what is gradient descent and whatnot. We will do that later. Then we can revisit what's the actual algorithm to run over this. Okay. For now, just know this is what linear regression is doing. And you can hopefully visualize it geometrically, and that's about it. Any questions? Okay, very good. So Q transpose, when you do them together, as we discussed at the beginning of lecture, they project down. Okay, so what happens is like this. Q transpose Y is kind of rotating, as you said, that is true. Then you multiply it with Q, it puts it on the span of Q columns. You can think about it that way too. Yeah, very good. That's all linear regression and projection stuff. Now we would like to do a little more. And we have time to do a little more, thankfully. Very good. Maybe before doing a little more, let me try to plant some ideas on your thinking that we will keep visiting during the course. Let's say I took my data, I ran my linear regression model, and I fit the best I could using a very good algorithm to do that. And okay, I'm ready now. Now I got my Q transpose Y and everything. Now somebody gives me a new house now. It's a new data vector and asks me to predict the price. Right? What am I going to do? I'll run the same linear model on it, try to predict the price. Literally, what I'm going to do is like I figured this weight, right? Weights are going to have as many coordinates as the features of your data. And I'll take your house vector, first feature multiplied with the first weight. Yeah, that's literally what I'm going to do. Sum it up. It will spit out a number. I'll say, this is my prediction, right? And then sometimes you will realize your prediction like is awfully wrong. Like it's not really close to what actual price of house was. What could go wrong? One thing that is very common that you should be always aware is something called overfitting. What does that mean? I trained my model so much, so carefully, that it ended up shooting myself in the foot. It's a little counterintuitive, that you did well, actually, okay? Your model fits to data you trained it on very well, perfect. But then you show it some data that the model has not seen before, it starts giving you nonsense. And the reason for that is like, your model is very well trained for the particular data it has seen, but now it became very rigid, very less flexible. And it's just fitting to the data that it has seen, but not doing anything well on some data that it has not seen before, okay? And then people try to come up with a lot of remedies for this. We will talk about some of them during the course. One thing that you will hear is called regularization, which we will see when we learn a little bit more of optimization. And there are many other tricks, but it's kind of hard to come up with something fully scientific for this, okay? So we'll see like something scientific, it gets close to understanding overfitting, but not like fully rigorously scientific. Because like, where do you stop your model, or what's really overfitting? You know, it's really, if you would like really take your scientist hat and like go in it, it's kind of hard to get a good answer. But you know, if you stop somewhere, like somewhere between a scientist and, I don't know, say here, right there is Sam Altman, that you don't want to be like that guy, and let's say here's a scientist, okay? Like you be, I don't know, like you stop 1/3 of the way, that's like reasonable spot. Don't try to get close to that. That's a very good analogy. Okay. All right. Thank you, Owen. Very good. All right. Yeah. All right. So now let's go for something new, but again, beware of overfitting. And we will try to talk about some remedies for that. This is one of the things that is most talked about in machine learning and data science. So likely you will already have some, you know, ways to check for this, but still it's something important to keep in mind. All right. Now we will need to go back to the singular value decomposition idea. That's going to be what gives us the PCA. But all right. So now, but before going to the PCA, we need to think about like matrices as an object. You know, think about a matrix like an array that stores your data. Yeah. And then how do you measure some errors in that array? Like, how does that array compare to some other array? You know, matrix itself is an object. Okay. So far, we are always working with vectors, actually, right? And we're using matrices to manipulate them. Matrices are moving them around. Matrices are projecting vectors down. Vector was our object. Matrix was kind of acting on it. Now, matrix could be an object itself too. Okay. A tensor could be an object itself too, but we will not go there. Tensors are a lot more complicated. But you know, if you're doing any machine learning library, you have seen tensors already. TensorFlow, or in PyTorch, you will do TensorDict, whatever, right? It's a tensor. Yeah. For now, let's stop with matrices. Okay. So we will not go beyond matrices. But let's say, how do I understand the matrix like as its own? Okay. So you could use singular values to understand your matrices as an object itself, also as a transformation, what it does to vectors when you give it to a vector. What was singular value decomposition? You take your matrix A and you write it as multiplication of 3 matrices, right? U, something diagonal, V transpose. How was that going? A was your M by N matrix. U was stuff that moved things around, orthogonal. V was again an orthogonal. And the thing in the middle is the singular values, okay? So this is the case if your matrix is like full rank, you will see all the numbers, no zeros. If it is not full rank, you will first see some numbers, then zeros. That's what singular value decomposition is. And when we talked about this for the full rank version, I also showed you some pictures. Yeah, here it is. This is a good picture to keep in mind about singular value decomposition, okay? So this is your matrix. You can think about it like first moving stuff around, then squeezing and stretching, then moving around again. Okay? And that singular values are how big are these axes, basically. Yes. Dimension for this example, nothing is changed. This is a 2 by 2 guy. It's got two singular values, so it's invertible. Dimensions staying the same. From here to. No. This is still supposed to be two-dimensional. Very good question. Yeah, so that's some bug in the picture, I would say. Yeah, sorry. It's supposed to be two-dimensional, okay? I don't know what the book I took this from was trying to do with this third line. Probably trying to see the rotation. Okay, so this is still two-dimensional. If it is confusing you, ignore this vector. Yeah, go ahead. Then that kind of stuff can happen, yeah. If it is non-square, sorry? Yeah, if it is not square, of course, you. Yeah, something like that, don't worry about it. So for now, this is your singularly decomposition. And now, let me take this mouse out of my way. Okay, very good. And if you take a vector x, and if you act on that vector with your matrix, and try to see how big or small is the output, it'll be like the biggest possible. How big was your x times the biggest singular value? That's the most stretching, okay? How small it could get, the smallest singular value. That's the most squeezing, okay? So the output will be always between these two numbers. So then the biggest one, sometimes this is called the operator norm of A. As I said, I did not come up with the names. Sometimes they will write A norm, A2, or sometimes A op. If you see anything of this sort, this is literally talking about the biggest singular value. How much your matrix can stretch stuff, okay? And then the ratio of this biggest and smallest, this is called condition number of A. What does that mean? You give it the vector x, and you look at the ratio of the biggest stretching divided by the smallest squeezing. How much change could this matrix can possibly do? And this is a very important quantity if you're trying to understand numerical computation using your A. Okay? Because whenever you're not running some discrete computation on your computer unless you're doing cryptography. Usually you would do some floating point, whatnot. And there will be always errors. And you want to know how much that error got amplified. When I took the vector, say, the first layer of my neural net, multiplied it with a matrix A. What happened, right? So to understand that kind of stuff, you will always see this quantity. Okay. We will not do numerical analysis in this course. I thought of doing 2 or 3 lectures on numerics, but then I realized there is not much space for this. If anybody is interested in digging more into stability and accuracy of numerical computation, I could give you resources and I'm always happy to discuss. Just we will not do too much. And this is getting more and more relevant lately, where people are trying to do what's called quantization in machine learning. They are trying to run computations on low precision to make it quick. But then how do you know the answer is actually accurate at all? Because you're, making low precision, that means you're rounding very, how can I say, too much rounding actually, right? So this is the type of stuff that gets into there, but I'm just giving you the vocabulary so that when you see it, you don't get confused, okay? This is what condition number is. And any linear algebra library you might be using, say in Python or wherever you like to do your stuff, they will already have implemented the condition number estimators. You'll just call the function. It will tell you how bad is your matrix. Do you know the golden standard for this kind of stuff? I'm just saying this because it's a rare occasion. LAPACK, have you heard of LAPACK library? So the guy who created initially a good chunk of LAPACK got a Turing Award like 2 years ago, Jack Dangoro. It's a rare occasion that academics did wonderful theory and also extremely good code. Usually academic code, don't quote me on this, but doesn't always run so well, because you don't have software engineers under your belt, etc. But in this case, this academics sit down and they wrote an extremely good library, and it's open source. LAPACK, LAPACK. It's a C library, and it's used all over the place in the backend. And it's free because some academics wrote it. And it's wonderful. Like, everything is extremely optimized. Last summer, I was trying to track down a function in LAPACK, then I realized it's using 26 more functions, and they're also optimized even more. And eventually, I gave up. I said, okay, I'm trusting what this guy did, because I wasn't sure if it is doing the right thing or wrong thing. Anyway, so it's that level good. So if you're just to be proud of some academic people, LAPACK is the gold standard for this. In Python, for example, it's very hard to trust numerical precision. For example, NumPy runs almost always the double precision in the backend. But if you're thinking like, I'm going to do single precision and my algorithm is still good, well, maybe it's doing double precision, you're not aware. So it's kind of hard to keep track in Python, at least for me. Maybe you guys are wizards on Python, you can keep track. Yeah, go ahead. It's a linear algebra package. Does all this stuff very well, computes all the condition numbers, everything for you already. You don't need to do anything. You just use LAPACK, done, more or less. Yeah. Yeah, everybody's using LAPACK under the hood. I'm just trying to pay the due respect to these guys. Nobody talks about them, but they did so much work for free. Okay. Now you can look at the biggest singular value, smallest singular value, their ratios. Well, you can do other stuff too. You can, for example, add all singular values to each other. Okay. This is the matrix analog of L1 norm. So we talked about L1, which was looking at if your vector is sparse or not. L1 is mostly caring about how many non-zero entries I got. And if you're trying to fit a matrix to somewhere, and if you want that matrix not to have so many entries, you want it to be sparse, this is the quantity you will use, okay? And it's called nuclear norm. Don't ask me why. And usually denoted this way. And this was a big thing for people who does compressed sensing. I think we have some electrical engineering background people. Maybe you heard of compressed sensing. This nuclear norm was a big deal there. Yeah, go ahead. Is the biggest singular value. Sigma n is the smallest. So which one, this one or this one you're talking? Yeah. So if this sigma n is a very small number, that means your matrix can potentially squeeze your vector a lot. Yeah. So So your matrix is, very good insight. So you're looking at the ratio to see if your matrix is treating one vector very differently than the other one. Because the smallest one corresponds to some vectors. It's squeezing some vectors a lot. Then sigma 1 actually corresponding to some other vector. And you literally see what is that vector when you do singular value decomposition. It's the first column of your U sigma VT, that first column of that V is the biggest one, okay? And then taking that first column and stretching it a lot, right? We are looking at the ratio, which tells you this matrix is kind of unpredictable. It's squeezing something a lot, stretching some other thing a lot, and the ratio is going to be a big number. Let's say sigma 1 is 100, the other one is 1 over 100. When you take the ratio, it's going to be even more. And that's going to be a big condition number. In lingo, they would call it ill conditioned. They would say, this matrix, you got to be very careful. So this is, I was talking about condition number, nuclear norm. Yes, it's going to be dominated by this big singular values. You're right. Exactly. So this one only cares about the big ones. And this making this small will make your matrix be looking sparse. you would get lots of zeros or small entries. And if that's what you want, that's what you could use. Okay. Very good. Okay, very good. Thank you. Any other questions? Okay, very good. And then the thing that you will see the most, since it is used the most, it has many names. The exact same thing has like, I don't know how many names. I'll tell you 3 of them. It's the exact same thing, okay? And it corresponds to square all that singular values, sum them up, okay? And there are many equivalent ways to look at this. That's why it's got many names, and it's one of the most commonly used norms, okay? Probably if you would change nothing in a package, this would be the default one. What would that mean? Like I take that singular values, I square them, I sum them up. And it's got 3 names, as I said. Some people would call it Frobenius norm, and you will see an F, norm F. Some people would call it Hilbert-Schmidt norm, and you will see an HS. And some people would call it trace norm. And those people would usually put at 2, okay? But this like summing up singular values doesn't give me too much intuition. I'll try to tell you what does this actually mean. Yes, go ahead. Yeah, so very good question. Well, what's up with the trace? I'll get there. Okay, very good. Very good question. It's called usually nuclear norm. Frobenius norm. It's a German name, yeah. And these are actually all Germans all over the place. Frobenius, Hilbert-Schmidt. I think Frobenius was in Berlin. Hilbert was in Göttingen. Hilbert was one of the few people who stand against the Nazis back in the day. So one should pay his due respect. And he lost a lot because of that, of course. All right, let's get back. He's one of the biggest mathematicians of 20th century. All right, so this is the trace norm, Frobenius norm, Hilbert-Schmidt norm. They're all the same thing, okay? And we will attach a couple of meanings to this. First one is very straightforward. Look at your matrix, right? Take every entry, square it, sum it up, just like doing your Euclidean norm to a vector, okay? This will give you this norm. One has to prove it. Don't worry about it for the moment, okay? This thing, square everything, sum it up, they'll give you exactly this norm. That's one way to look at it, okay? So far, so good. So this is like the most natural thing to try. Take your matrix, square every entry, just like our Euclidean stuff we are used to, sum it up. This is the norm you will get. Very good. Now, what's up with that trace thing? So Adam asked a very good question. And that's exactly what I was writing to myself when I was writing these norms. What's up with that trace? So far, so good. So this is what it is. I think there's a question. Ask me. Go for it. Okay. You're making sure he's still sane and good. This is the same thing, right? Yeah, very good. Yeah, this is intriguing, just that I have limited time, unfortunately, and I want to do PCA today. So yeah. Okay, what's up with that trace stuff? Well, so what is trace first? Trace means trace of a matrix. If this is your matrix with a whole bunch of entries, you take the diagonals, you sum it up. That's called the trace of a matrix, okay? You only look at the diagonal, nothing else, and sum it up. It's like if you're taking trace of something that happened. You're not looking at the entire matrix, you're just looking at the diagonals, okay? Okay, now off of trace, people defined an inner product for matrices. Remember when we had vectors, the inner product was the thing that gave us angles. Right? Now for matrices, if you have the same notion of an inner product, that's going to be useful to compare them as like data arrays. You know, remember, let's say we talked about using inner product and then get the angle from there and then do this cosine similarity, right? That's what people do all the time to compare vectors that corresponds to words, you know, word embeddings. What's something behind a lot of stuff? You take words, you make them into big vectors, and then compare those vectors using the stuff we are talking about to think about if they are similar or not. And depending on how you turn them into vectors, your similarity notion might be capturing semantic similarity between words, maybe not, blah, 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 okay? So this is what this, I said blah, 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 just because I don't have time. Otherwise, it's something important, okay? Right. And if you just Google vector databases, you will see how important it is, okay? So there will be a whole bunch of companies coming up just selling better vector databases. A whole bunch of startups in Silicon Valley. All right. Huh? I mean, if you have done any computational geometry, you work on it without intention. So I was always interested in computational geometries. So yes and no. So I did not work in the context of word embeddings. Yeah. And the buzzword, if you're interested in, is approximate nearest neighbor search, ANF. If you want to be fancy on interviews, look it up before going to interview. Approximate nearest neighbor search, you can impress them. Likely your interviewer may or may not know. Maybe knows, then they'll be impressed. If they don't know, they'll be even more impressed. Okay, so let's get back. Okay, now, focusing again, I take two matrices, A and B. I do B transpose A. This is yet another matrix now. And I look at the trace of it. Okay. Turns out this defines a nice inner product. Again, you have to check if it is actually a nice inner product or not. Right? And as soon as you have an inner product, that also gives you a notion of a norm. Right? If you have an inner product, x times x inner product square root is the norm. And this norm is exactly, again, the same norm right here. Okay. So three things are actually equal to each other. The singular value stuff, the squaring everything, summing up stuff, and then this trace inner product stuff. They all give you the exact same norm. That's why this thing has many names. Depending on which angle you looked at it, you defined it a different way. Your name gets attached to it. Okay. All right. These are all the same norm. That's why it's sometimes called trace norm, sometimes Hilbert norm, sometimes Frobenius norm. This is what it is. Okay. For us, the good thing is this norm is also coming from an inner product. Now I can do all my tricks. I can think about orthogonality, orthogonal projection, whatever else if I want to. Not only on vectors now, also on matrices. Okay. And doing these tricks on tensors became much more complicated than people expected. So I'll not get into that. Okay. But I love that stuff. Okay, I've written some papers, but not for this class. But if you're interested, I'm always happy to do. Right. All right. Okay, so far so good. Now let's. I think I want to skip over this thing. I was gonna do a little something important, but not terribly crucial for algorithmic purposes. Is like thinking about when a matrix will have the singular values and eigenvalues the same. Okay. So if you remember, singular values are always 0 or positive. Eigenvalues could be negative as well. For them to coincide, all your eigenvalues has to be non-negative. And that type of matrices are called positive semi-definite matrices. And they're important and all over the place, but I'll skip over for the sake of time. Yes, Farhan. Yeah. 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 Let me see. So if you think about your geometry using this norm, I'm kind of giving you a cheater's answer now. That literally looks orthogonal, that kind of matrices. Okay. So the fact that this is an inner product allows you to attach geometric interpretation. Okay. Now what you will do is like you multiply two matrices. If the summation of the trace is 0, in this sense, they will look orthogonal. And another way to think about stuff orthogonal is they are unrelated from the perspective of this inner product. Okay. The whole B will be unrelated to whole A, not particular columns one by one. A little more complicated than simplifying that way, but we can discuss more later. But very good. These are good questions. Keep them. Visit me. We talk about it. Talk to people. Very good questions. Just I need to take them Later, not now. Okay, now let's go for the PCA. All right. Very good. So for PCA, we have a wonderful notebook. I will upload it to our Canvas today after the lecture also goes there. So, make sure to look through the notebook. It has nice explanations and some applications for the particular data set. So what is PCA? It stands short for Principal Component Analysis. Okay. What does it even mean? You have a lot of data points in suppose high dimensions. Rn say they have a lot of coordinates. Okay. And what you would like to do is like intuitively say, if you could find out what are the most important 5 coordinates, you would be happy, right? Maybe that's not that simple though. Maybe you have to combine coordinates and make 1, combine another, make 2. This way, like extract 5 clever combinations of all your coordinates. It would be super nice if there's like 5 of them. Yeah, pick these 5, you're good. But usually that's not that simple. But what you could try, a little more, a little less naive than that. Okay, let me find a clever combination of all my features, but not only one. In regression, we were finding one combination of the features, and that was our model, correct? Now let's say I want to do like 10 of those. That's the D here. You get to pick your D. Your data is living in a high dimension, and you want to find the best D-dimensional subspace of that big thing to fit your data. What do you mean by best? Here, our notion of best is the following. Suppose I was living in 100 dimensions, and my D is just 2 dimensions, okay? And then I'll take your 100-dimensional vector, project it down to my 2 dimensions. That's going to be what comes out of it. I will look how much I lost, sum it up. That's my notion of best. The smallest error fit, okay? Now I'm literally fitting the best D-dimensional subspace I could. That's the idea of PCA. So somehow this best D dimensions will give me the most important D components. That's the idea. That's why it's called principal component analysis. Yes, go. No, that will be still like in regression, the whole thing is just one number at the end. So it will correspond to this D being 1, essentially. You're kind of trying to find like the best 1 D combination, if you think that way. But I would say split regression and PCA on your head. These are kind of 2 different things. Okay? Because in regression, we are trying to predict that label. That's what we care about. That's all we care about there. Yeah, I have a whole bunch of features. I don't care about your features. I care about the price of the house. Here, that's not the story. I have a whole bunch of features. I care about them, but they're just too much. I'm trying to pick a D-dimensional synthesis, somehow like the principal ones. Okay? So I would say try, at least in my mind, I try not to make those 2 images, mental images, confused with each other. Okay? Because they're kind of 2 different things. But the math behind will be very similar. Okay. So now that's what we want to do. I have, I don't know, data living in a huge dimension. I want to find like a smaller dimensional thing that fits my data the best. If all my data would be in a small dimensional thing already, then I'm good. What does it mean? Let's say, just for the sake of discussion, suppose your data is 2-dimensional, but they all apparently living on a line. Let's say n is 2. All these dots, they have 2 coordinates, right? But I fit them a 1-dimensional thing. Just because the nature of the data I had, even though they were 2-dimensional, they were all living on a line. Now I could just think about them using that line. Okay? But this is, of course, rare, right? That's not going to happen. But that's kind of the intuition. Can I find like a, maybe not 2 and 1, but like maybe data is like 10 dimensionals. Maybe can I find a 3D thing that gets close to fitting it, and gets close is this. If this error is 0, you fit it perfect. The small you could make is the best, okay? So how am I going to do PCA? I will attempt to show you the derivation of PCA. Let's see if I manage in 15 minutes. I have about 15 minutes. I enjoy doing this, but let's see if we can do it. Okay. So because people give PCA like a magic, it's not magic, okay? That's going to be the main punchline of the discussion in the next 15 minutes. And as I said, you have a notebook playing with it, and that's about it, okay? So how do you derive PCA? First, simplification. And sometimes this is assumed in the implementation you're using. The average of your data points is the origin. Okay, so your data points are here and there. If you take the average, maybe it's not the origin, but you could always shift them to put the average on the origin. Okay. So one has to be careful if this is assumed in your implementation, the library you're using, and if your data is not centered, first center it before doing PCA. Just check, all right? I will, in the mathematical derivation, I will assume this is the case because you can always do this. Okay, that's the first simplification. And the second one, just like thinking about the best d-dimensional thing is a little abstract for me. What I would like to think about is like, give me the vectors that span that thing. Okay, so instead of give me the best plane, give me the best two vectors. I'll look at the span and see the plane. Okay, that's my second simplification. So I'm going to be looking for a matrix with d vectors in it, and that's going to be my best fit thing. Okay, so I'm going to use this matrix like we were doing for the projection. Okay, suppose even that is orthogonal. I have an orthogonal basis right now. Okay, give me your best orthogonal matrix, which has got d columns, and when I use it for projection, my error is the smallest on the data I have. That's what I'm going to try to do. Find the best orthogonal matrix, find the best projection. Okay, so far so good. So literally, this is your projection. Take this minus x, square, sum it up. That's our error right here. So now problem got simplified, at least in language, for searching for the best orthogonal matrix. Okay. That respects my data somehow. All right. How do I formulate it? Well, find the best orthogonal matrix, and by D. Orthogonal means if you do transpose on itself, you get the identity. You know, W transpose W is the identity, that's the orthogonality. When you do W transpose, that's projection. You know, that was a very good point. Okay. And then this is now my projection. I'm taking it minus my data. I'm squaring it, you know, the norm and whatnot. And this is my error notion. I want to minimize this. That means this particular guy, among all possible choices of d-dimensional subspaces, should be the one that minimizes the error. That's like the best. That's what I want for PCA. Okay. So far, so good. Okay, how do I find that orthogonal matrix? Of course, that's the question. Or what does it correspond to? Well, let me see how much of this math I want you to see. All right. So you do the math I was doing here. You don't have to, you know, depending on your taste, this might be like, don't see the sausage and the laws before it's made, or you want to actually see the algebra, so it's up to you. Okay, so this is now being recorded. You can read this, or maybe, I don't know if I'll type it, maybe I'll type it and give it to you. But the punchline is, if you go to that objective that we were talking about, this was our error notion, you do a whole bunch of algebra, and it ends up being the same as the thing on the right, turns out. You do your first vector, identity minus that thing, times the vector again. That apparently is the same thing as this. It's not clear. You have to work it through. That's the page I skipped over, okay? So if you take my word for it, this is your objective function. And you want to find the W matrix that minimizes this. Okay, still not clear to me. How am I going to find that matrix? I'm just phrasing the objective function in a different way for the moment, okay? Now, if I could phrase this objective function in terms of something of my data matrix, when I stack all the data into a matrix, if I could see this in terms of that matrix, maybe then I'll understand, okay? And what happens is, turns out, if this is your data matrix, capital N many data, they all got N coordinates. And this thing, identity minus W transpose. Don't forget this is n by n. The other way around, W transpose W was the small guy, okay? And then this is your data matrix again. If you do this multiplication, so the transpose shouldn't be here. And if you look at the trace of the end result, apparently that gives you exactly the objective function you were looking for. This is again more algebra. There's some algebraic miracles happening. But at the end, turns out the error we were trying to minimize literally corresponds to take this matrix, multiply it from left and right with your data matrix. You will get something out of it. Look at the trace. That's what the error is. And now when you get there, things start getting easier. I'm trying to minimize this trace. Well, let's look at it. X transpose identity, X right here. X transpose this stuff, an X and a minus. This is what I'm trying to minimize. Trace is a linear thing you can split. If this is a fixed thing from your data, your choice has nothing to do with it. So minimizing actually corresponds to minimizing this minus this stuff, right? Minimizing a minus is the same thing as maximizing the thing. Okay, you're trying to literally maximize this. X transpose your stuff. Okay, very good. And now remember, trace gives you an inner product. So if this would be a matrix A, what would be A transpose? This would be A transpose. And this would be literally inner product A with itself. Or in other words, norm of that A squared. So in other words, I'm trying to maximize norm of this guy. This is my data matrix. I'm trying to find an orthogonal matrix. It's n by d. To transpose is d by n. Okay. My big matrix here, this guy is n by capital N, yes. Exactly. You're trying to preserve the most you can. Exactly. So at the end, we did all the math. It boiled down to this. Now it's much more simple to understand. This is my data matrix. It's a huge thing. So let's remember how big was this X. It was n times capital N. N is the number of coordinates. Capital N was number of data points. Okay. And I'm trying to find the best D represented by this guy, so that when I kind of project it down, it's going to preserve the most of my data, whatever it was, okay? And that corresponds to maximizing this. Now, and if you remember, this also had the other singular value representation. This is now a D by N thing. So it's got D singular values. This thing is literally summing up all that singular values and squaring them, okay? All right, so far so good. And now I'm trying to see this in terms of the singular values of my matrix X. This is your matrix X. This is the singular value decomposition. It's gonna have n singular values, then a whole bunch of zeros. Remember, the data has n coordinates, but you have a lot more data than the number of coordinates. Coordinates was already big. Let's say you had 100 features and you had 2,000 data points. So when you do the singular value decomposition, you will see 100 singular values and a whole bunch of zeros. And among the 100, you are trying to pick the best D, whatever was your D. Among the 100, you are trying to pick the best 5, say. What is the best 5? If you are trying to maximize the thing. Well, pick the biggest ones, right? Pick the biggest D stuff from here. That will be what you expect to do. And that's exactly what PCA is. You do the singular value decomposition of your data, okay? And then you look at the biggest singular values, and you look at the columns corresponding to those singular values, and you project stuff down there. That's it, okay? Literally, your mysterious D will be given by pick the D best singular values, And if you survive through all this explanation, you might be feeling like this cat. So that's about it, okay? That's what PCA is. So once again, it corresponds to take your gigantic data matrix X, do the singular value decomposition. Since you want to preserve as much as you can, pick the vectors that corresponds to heaviest singular values. If you want 10 coordinates, then pick the 10 heaviest singular values, okay? And literally go to those vectors in your U right here. First 10, that's your projection, and that's your best fit linear subspace, okay? Now, when we learn a little bit of probabilistic language, we will attach even one more interpretation to PCA, which is when you look at your data and try to understand the directions that preserve most of the variance. If what I just said doesn't make sense, that's fine. I did not define variance yet. I'm just telling for the people who heard of it before. So PCA also corresponds to best directions that preserves most of the variance of your data. We'll also talk about that. So it's an optimization problem, and it is solved by singular value decomposition. Just do the singular value decomposition, take the top columns, you're done. Of course, again, this is what mathematically it is. Algorithmically, you probably don't want to do that singular value decomposition for a gigantic data matrix. There are mathematically equivalent, algorithmically better ways. That's what you would do for PCA. Yes, questions? Last minute or two. I think someone had a question, but I don't know who was that. Okay, so this is how you derive PCA. And I'll not redrive it, don't worry. You'll not have the pain of last 10 minutes again. But I think it's a worthwhile thing to at least know what it is. It's literally the best subspace you could fit. And it literally corresponds to singular value decomposition. Yes. We are going to touch base on what you just asked again. So remind me that question. Okay. Yeah, we will see more dimensionality reduction tools later on in the course. That's what the question was about. This is not the only tool to reduce dimension of your data. It's just a tool. All right. That's about it. Thank you so much.